Good afternoon, everybody. Today we will discuss remote sensing in GIS applications in irrigation water management. So, if you see, irrigation is not a very new subject. Irrigation is as old as human civilization. Archaeological findings suggest that there are traces of irrigation system even 6 million BC before Christ era. Where in Mesopotamia and Egypt, where barley crop has been grown, which is a water intensive crop. So the question comes, why we need the irrigation? So we need irrigation in the arid and semi-humid regions where rainfall is either insufficient in amount, spatially varying, temporally varying. So it doesn't support the actual water requirement of your crops. So we need artificial supply of water, which we call irrigation. We can provide irrigation to safeguard our crops against the frost, or we provide irrigation for increasing the production of our crops. So if we discuss the irrigation thing now, the topic here is remote sensing application in irrigation. So first of all, we start with the irrigation project. So what would be a project? Is a specific activity defined in time, location and the means. So if you see the project cycle, this is a specific project cycle. This is a project cycle of any project. Now I am discussing about irrigation project. So the cycle starts from project identification and definition. And why I am showing this? Because every step in the project cycle will have a partial or complete role of remote sensing, be it first stage or the second stage, project formation and preparation, feasibility analysis, the design of that project, appraisal, the site selection and negotiation, then project activation, implementation, even the project evaluation. And this result of this project evaluation will go as a follow-up analysis as an input to your new project activity. So why I am discussing this? Because we believe that remote sensing has a role in each of these stages. So now, what is the planning? Planning aims in the optimal use of all available resources. And when I'm talking about using the resources, first of all, mapping or quantifying these resources is very important. And as we all know, in this particular area, mapping the resources, mapping the natural resources, remote sensing has tremendous role to play. So we'll skip upon this and we'll start the main topic. So the question comes, what is actually the irrigation water management? If we are able to answer these questions, how to irrigate, how often to irrigate, and how much to irrigate properly, if we are able to answer these questions, we are actually managing the irrigation water. So what gives answer? What techniques gives us the answer of these questions? The first is irrigation techniques. So irrigation techniques tells us how to irrigate. Irrigation schedule tells us how often to irrigate. And the crop water estimation or irrigation water requirement assessment tells us how much to irrigate. And all these things you can decide, you can derive using remote sensing and GIS inputs. So, in other words, the irrigation water management is the process of determining and controlling the volume, frequency, application rate of irrigation water in planned and efficient manner. And to start with, so first of all, we need to know how much irrigation water we require. So we need to quantify the crop water requirement. So crop water requirement or irrigation water requirement will be the crop water requirement plus water losses minus the effective rainfall. So we have to calculate the crop water requirement, we have to calculate the water losses, and then we can know the irrigation water requirement. So we'll start with estimation of specially distributed crop water requirement using meteorological data and remote sensing input. So to describe this, I'll take help of a case study of Mahi command area from Gujarat, wherein we have used a multispectral WIPS data, multi-temporal WIPS data, and we have tried to estimate the crop water requirement and irrigation water requirement of this command. So we have used the WIPS data, the meteorological data where we use average temperature, sunshine hours and relative humidity. We have used the FAO Benny-Tudor method to calculate potential evapotranspiration. So you can see this is a flow chart of this method. Multispectral data is being georeferenced and atmospheric corrections have been done. Then using hierarchical classification technique, the type of vegetation or crops have been identified. The vegetation indices of each and every pixel were derived. Parallelly, using metallurgical data, you can see evapotranspiration, potential evapotranspiration has been calculated and it has been interpolated. So now we have a crop map, its vegetation index and the potential evapotranspiration. So now we have to decide what is the Kc of each crop and we have to multiply that Kc with the Et to get the crop water requirement. Excuse me. So this is a flowchart of a hierarchical classification technique. We have used a threshold technique to classify the vegetation area to non-vegetation area, and among the vegetation area, different crop types. Using this, we have classified the entire land into different crops. Now, because we were having only one metallurgical station at the center of this command area, so we have calculated the potential evapotranspiration, and using inverse distance weighted method, we have interpolated this. And you can see here, we have taken the Kc, crop coefficient value for all these crops, the early wheat, late wheat, and the perennial crop from the reference literature. So from reference literature, for each of this Rabi month, what is the standard Kc value we have taken out. But the point here is these are only reference values. We cannot tell in which pixel this value is true until unless we have the crop type map. But even with crop type map, the condition of crop varies. To know what Kc should be applied for every pixel, what we have done, we have tried to relate the vegetation index with the crop coefficient. Because if you plot the vegetation index and crop coefficient, both of them follow the same phenological curve. Your vegetation grows, your Kc grows, and after maturity, your vegetation vigor comes down and your Kc also comes down, which you can see here. These are the vegetation index values, and in previous slide, we were seeing the Kc values. It's same. It goes on increasing at maturity. After maturity, it again drops down. Same you can see here. The Kc value or the vegetation index value go on increasing, and after maturity it will drop down. So this tells us that there could be a linear relation between coefficient and this vegetation index, and this assumption we have exploited here to derive a relation between crop coefficient and vegetation index as a linear relation. And this table shows us the relation, the slope, the intersect, R square, and the standard error of those relations. So now we have for 4 crops the relation between vegetation index and the crop coefficient. We already have specially distributed evapotranspiration value. So now what we have to do, we just have to convert the vegetation index map into Kc map using these relations and multiply this Kc map to the potential evapotranspiration map, so that we can get the crop evapotranspiration or crop water requirement, and this kind of crop water requirement, seasonal crop water requirement, we can get. If we compare this, you can see now all these are the canals which are masked, so they are getting the highest value. The crop condition here is very poor, so the irrigation water requirement or crop water requirement is very less. But we have to take into account that if we calculate the crop water requirement or irrigation water requirement using remote sensing technique, we are always bound to get under prediction. So we have to offset to cover this. Now this was the simple technique using remote sensing data just to convert the vegetation index into Kc. Now there are some modern techniques to calculate crop water requirement or evapotranspiration. All of them falls under surface energy balance approach. One exercise I am trying to show you here, where we have used this surface energy balance approach to calculate evapotranspiration. So it basically says that, whatever energy we are receiving, this is the net radiation that we receive, will be used to heat up the atmosphere, to heat up the soil, and rest of the energy will be used for evapotranspiration. So the total energy that we receive in terms of radiation will be used to heat up the atmosphere, which is a sensible heat flux of atmosphere, to heat up the soil, which is a sensible heat flux of ground, and the remaining energy will be used to convert water into water vapor, which is a latent heat flux. So the problem with latent is we cannot measure it directly using any instrument, so we have to calculate it. So we try to equate this. So we are saying Rn, which is the net radiation, minus ground heat flux minus atmospheric heat flux tells me what is the latent heat flux for the evapotranspiration, and we will try to solve it, and in this process we will get the total amount of evapotranspiration. Now to solve this, we have to solve the 4 terms, or I can say 3 terms. So I will get evapotranspiration. I have to solve for the net radiation, I have to solve the ground heat flux, I have to solve the atmospheric heat flux. So we will do it part by part. Now if I have to calculate the net radiation will be consisted of 5 components: the incoming short wave radiation, the reflected short wave radiation, the incoming long wave radiation, reflected long wave radiation, and the emitted long wave radiation. Because the Earth's surface will be at 300 degree Kelvin, and the law says any body above 0 degree Kelvin will emit energy in terms of electromagnetic radiation, and the wavelength in which maximum amount of energy is emitted is inversely proportional to the 4th power of the surface temperature. So the Earth's surface temperature is 300 degree Kelvin, so it will emit energy in long wavelength region, whereas the surface temperature of Sun is something around 6000 degree Kelvin, so it emits maximum energy in short wave. So I have 5 components to solve, which are short wave incoming, long wave incoming, short wave reflected outgoing, long wave reflected outgoing, and long wave emitted outgoing. Now as you can see, albedo is nothing but reflected outgoing divided by reflected short wave outgoing divided by short wave incoming. So I can calculate this, I can solve this short wave by just saying total short wave radiation is equal to 1 plus albedo into incoming short wave. Now the long wave incoming will be the energy which we are getting from Sun, and it is transmitted through atmosphere. Solve this long wave outgoing and reflected outgoing. So how to solve it? This is a flow chart. We will have a remote sensing data where the information is given in terms of digital number. So it will be here, somewhere here. So from those digital numbers, I will convert the entire bands into spectral radiance. Then from spectral radiance, I will calculate reflectivity. From reflectivity, I will calculate albedo at the top of atmosphere and the surface albedo. Then I will calculate incoming short wave radiation. Now to calculate incoming short wave radiation, I need a very simple information, that what time of day is it, and what is a Boolean day, and the atmospheric transmissivity. So all this information will be available in your remote sensing header file. Remote sensing header file tells you at what time it is being acquired, what is solar elevation angle when the image is being acquired, at what Julian day the image has been acquired, and because we are using optical remote sensing data, we can assume that there is a fairly good atmospheric transmissivity because we generally don't prefer the cloud covered data. So all this information will be available to you. So using this, you can solve the total net short wave. For long wave, we have to calculate the emissivity. Emissivity in narrow band, emissivity in broad band. For that, there are empirical relation between NDVI or emissivity, soil adjusted vegetation index and emissivity, leaf area index and emissivity. So either one of this relation you can use to calculate emissivity from the vegetation index values. Then you need remote sensing data where the data is being acquired in thermal bands also to calculate the land surface temperature. Now from land surface temperature emissivity, you can calculate the outgoing long wave radiation using simple Stephan-Boltzmann law. Then incoming long wave radiation you can calculate if you know the near surface atmospheric temperature, and you can solve this entire net radiation. So now we have Rn. To solve this ground heat flux, there are empirical relations available which tells you that what should be the G by Rn ratio if this is your land use class. You can use them, or there is a detailed relation between G by Rn which requires the surface temperature, the albedo, and the NDVI. All of this information is already available with us, so we can calculate this ground heat flux. So we have solved the net radiation, we have solved the ground heat flux. And now one component remaining is the atmospheric sensible heat flux, which you can calculate if you know the rho density, the specific heat. This dt is the near surface temperature difference, and Rho is the aerodynamic resistance transfer. This particular term will appear in your Penman-Monteith equation also. So to calculate this, I require two heights. I require the frictional wind velocity, and this is a von Korman constant, which is 0.41. To calculate this, I also require the vegetation height, so which you can derive if you have the land use map. Now using this, if I am able to solve this equation, which says that evapotranspiration is equal to Rn minus G minus H, I will get the evapotranspiration, and because I am calculating this evapotranspiration using optical remote sensing data, which is an instantaneous picture of energy balance, I cannot say that this is a daily evapotranspiration. To convert this into daily evapotranspiration, I need this reference daily evapotranspiration. So what I will do, whatever instantaneous evaporation I have calculated for every pixel, I will convert it into a term called reference evapotranspiration fraction, which is similar to the crop coefficient. So now I have a crop coefficient, I have a reference evapotranspiration from meteorological data, so I can convert this reference evapotranspiration into actual evapotranspiration of any time period. If I have reference evapotranspiration of R, I can convert it to hourly evapotranspiration. If I have daily reference evapotranspiration, I can convert it to daily evapotranspiration. Weekly, I can convert weekly crop water requirement. So now the one part, knowing how much is the crop water requirement is done. But there is another thing, we need to know the source side also, how much water is available. Now generally most of the irrigation projects are supplied by suppliers, and we need to know real time. I have to plan for next month, so I need to know how much water is available at this point of time, so that I can decide how much I can supply for next month. And generally in all the reservoirs, there will be multiple users, like the reservoir water will be used by some municipal corporations for drinking water supply, some industries for their water supply, then for hydropower project, and then for irrigation also. Though our water rights say that irrigation will have a second priority after drinking water, but the amount required by every user has to be taken into consideration. So simple application of remote sensing could be, if I just monitor the water spread area in the reservoir, I can always compare this with the area capacity curve. So what I have to do, every reservoir will have an area capacity curve. Elevation area will tell me how much is the water available, capacity of that reservoir. So I just have to monitor the water spread area. I just have to know what is the elevation of that water, and real time I can get how much is the capacity, how much is water available in the reservoir, based on which I can plan the irrigation schedule for my next month or next season. Now, after knowing the demand, after knowing the supply, the point is I need to know how good my infrastructure is, how good my irrigation distribution network is. I do have a demand from farmers, I have ample amount of water available in my reservoir or my river, but the distribution will be done through my infrastructure, irrigation infrastructure. Maybe it's a closed conduit structure, maybe it's an open canal infrastructure. We'll discuss about open canal infrastructure. Now if my distribution network is faulty, I will not achieve my objective. My objectives are to give irrigation to increase the production of my command area of the agricultural production. But it will not be achieved if my irrigation infrastructure is faulty or not adequate enough. So I need to monitor it, and I need to monitor it dynamically. It is not that I have monitored this irrigation infrastructure a decade back and I am presuming that my infrastructure will have that same state, because the infrastructure changes. If the canal is not working, it is bound to change the shape due to siltation, or maybe it will get destroyed, destructed, or even if the canal is lying, with time the fractures will be generated, so the losses will be more, or there could be many things which can happen with the canal. So I have to monitor my infrastructure dynamically, so that I should know where my infrastructure is functioning well and where it is not functioning well, where I should concentrate my efforts. So you can see here I am showing you the index map. This is not to scale, not georeference index map of your area. So I cannot tell you, if you tell me that which farmer will get water from this particular canal, I cannot tell you, because this is not georeferenced. To know this, I have to go to field. I just have to scroll through the records. It's a laborious process. Then only I will tell you, okay, if this farmer is getting water or not. But if I convert this in terms of geospatial data, then I just have to run a simple query which will tell me, okay, if this is a farmer, so this farmer owns this land, and this land falls under this particular farm, and this farm, is it under ICA or not? ICA is the irrigable command area. So if the land is under irrigable command area, the farmer will get water from this miner, and if it is not, he will not get. So you can see this is a Cartosat 1 data of the same area, and you can see how good the canal network is coming out. So now I have to convert this image into a database. So I have to digitize this entire canal network, and if I have to digitize the canal network, if I map the command area, the question comes, what kind of data I should use? Now we have a plenty of options with us. We have EVIPS data, we have listed data, we have list4 data, we have Cartosat data. So which kind of data I should use? Now the decision will be based on what are my objectives. Now if I am interested in mapping my main canal, or if I am interested in mapping my crops, I should go for coarse resolution data, which will give me more repeatability, because crop is a dynamic, it's a temporarily varying feature. So I cannot acquire one image and I can say that, okay, I can map the crop type, because crop will vary, its phenology will vary. To map that phenology, I need temporal remote sensing data. So I will focus on AVIPS. And why I am saying AVIPS is good enough to map main canal, because all the main canals have width something around 50 meter, in the range of 50 meter or 100. So that will be easily, you can detect that. Now you can see this particular line is a canal. This is Upper Ganga canal, and which I can digitize using even a AVIPS data. But if I am interested in mapping main canal, branch canal and distributory, maybe the distributories will not be of that much width. Distributories may be of 10 to 15 meter width, which will not be detectable in 56 meter resolution. So I have to go down to 23.5 meter resolution, which is a listed data. So if I am getting a better special resolution, I have to lose the temporary resolution. I can get a WIPS image for my area every week. But to get a list of my area, I have to wait for maybe 20 days, repeatability. Now, if my interest is of mapping main canal, branch canal, distributory, maybe a major canal, which is of width 5 meter, I will go for list4 data. As the resolution increases, and special resolution increases, the temporal resolution will be poor. Then if I am interested in mapping the command, mapping the infrastructure down to the sub-miner level, which may be of width 1 meter or 2 meter, I will go for Cartosat series. Cartosat 1, if I know the width is within range of 1 or 2 meter. And Cartosat 2, if I know my my sub-miner is of the range maybe sub-meter, then I will go for Cartosat 2 series data. Now you can see, I am just showing you here, there are more like Cartosat tiles around, and these blue lines are the entire canal network which I have digitized using Cartosat 1 data. This is a Mura command in Ahmednagar district of Maharashtra. Entire network we have digitized using, this is a Mura reservoir, and this is the Aurangabad Dhaneshwar Sagar reservoir. So the entire irrigation network we have digitized using Cartosat data. And then we have collected the attribute information like the name of canal, the length of canal, the design, discharge, and all other attribute information which we are interested in, and we have kept that information as an attribute table of all these canal layers. You can see here the name is there, its site is there, type is there, what is the chain age, its length, all this information is being stored, and this comes under the mapping of irrigation infrastructure. Now I have mapped the irrigation infrastructure, but this thing is not only limited to having a database. Now government has gone one step ahead, and using, like I told you, in project cycle, we have an application of remote sensing in every stage. In project cycle, there is a monitoring phase also. When I implement that any irrigation project, I need some mechanism to monitor the progress of that project. So this can also be done using remote sensing. A simple case study I am showing you here, where Government of India has given ISRO a project called Accelerated Irrigation Benefit Program, AIDP funded irrigation project monitoring. So what we have done in phase 1, we have monitored 50 projects. In phase 2, we have monitored 50 projects. The projects which were getting money from AIDP to fill the gaps, fill the critical gaps to increase the irrigation potential. So the objective was to monitor the progress of those projects. So I'll show you a case study. The deliverables of those projects were, we were supposed to give them the Cartosat, the CWC was the nodal agency, so we were supposed to give the Cartosat satellite data to them. Then the A4 size map of that entire command showing the irrigation potential created and the dips and everything, and the report also. So we did this exercise for Eastern Ganga Canal project, Madhya Ganga Canal project. So I'll discuss about the Eastern Ganga Canal project, where I'll cover the mapping of irrigation infrastructure and monitoring of how it can be done using remote sensing. So you can see, I'll skip these slides. So this was the data used. We have used the Cartosat 1 orthorectified data. We have used the index maps which were not to the scale, which were not georeference. Then index maps provided by irrigation authorities. In some cases we got the line diagrams. Line diagrams are better than, because line diagram tells you the change at which the particular canal operates and on what direction, on left or right direction the canal operates. Then the reports which we can get from the CWC and the irrigation authorities, and we have relied most on the field surveys that we have done. So this is a silent feature of Eastern Ganga Canal project. We will not go into this. This is a Cartosat data which has been acquired to cover this entire Eastern Ganga Canal. You can see the entire command is being acquired by almost how much? 36, 35 types of Cartosat data. Now ancillary data, as I discussed, the index map, the T diagram and the reports. We have collected the field data. I will go to so this is the flow diagram which we have followed. So we have digitized the canal network, we have added the attribute information, and then we have checked what is the promised or design length of a canal and how much is the actual constructed length. And it's not only the constructed length, but how much of that length is hydrologically connected to the source. Like the main canal source will be reservoir or the diversion structure, which is a barrage. But after the main canal acts as a source for the branch canal or the distributary, which is taking water from that main canal. So I need to know if the branch 1 is designed for 50 kilometer. Is the branch 1 actually being laid down for 50 kilometer, and is the entire 50 kilometer hydraulically connected to its source, which is the main canal? So this we have checked in this AIDP. So I'll show you diagrammatically what we have done. So you can see few cases wherein this is a canal 1 where the promised length or the design length was 2 kilometer, whereas you can see here the actual constructed length is 1.95 kilometer. There is a gap of 0.05 kilometer only, but the gap is between here. So physically, actually the physical, if I take the percentage will be very high, the completion percentage will be very high. Whereas if the gap exists here, the entire length after this gap will not receive water. So actually, practically, only this much is the hydraulically connected length. So the completion, if I have to check, it will be, let us say here, the completed length only will be this portion, and then I will calculate out of promised length how much is actually completed hydraulically, and that much is the only completed project, and then that percentage I will multiply to the promised ICN. I'll tell this is the actual generated irrigation potential, and remaining is the balanced irrigation potential. Now in this case you can see the same problem. The promised length is 2 km, the completed length is 1.95 km, only 0.05 kilometer gap exists, but that gap exists at the head reach. Entire 1.95 kilometer canal will not receive water until and unless this canal is being connected to the main supply. So this is zero IP, zero irrigation potential achieved. Now in this case, actually the entire canal which was promised or which was designed is being complete. So irrigation potential achieved is 100%. The same what is being promised is being achieved. So this is how we have first digitized the canal network. We have generated tool in our GIS wherein we have to provide GIS canal network, and it will run the network analysis module. So it will calculate the length of each gap, whether the gap is being hydraulically connected or not. The same module can be used, or this kind of modules are available free of cost online also. Now I am trying to show you how it appears in remote sensing data and how it appears on field. Now this one is the main supply canal. I mean this is a main canal of Eastern Ganga Canal project, and this is a Kandi map. Can we start? Okay. So sorry for the interruption, and I think few of us lost the AV during this slide. So I would like to quickly repeat. So what I was saying, that using Cartosat data, what we have done, we have digitized the entire canal network. Now it's not the physical length which is important, but the hydrologically connected length is important to knowing how much is the irrigation potential created. As we can see, this is a minor one, where the promised length is I think 2 kilometer, and the actually constructed length is 2 kilometer, and this entire canal is hydraulically connected to its source. So this is the source of water for this minor. So I will say the physical progress of this canal is 100%. So the irrigation potential which is designed for this canal is being achieved. So let us say this canal was designed to irrigate to 250 hectares of land. Since its design length is being achieved, so I can say that the 250 hectares of land will get water from this canal. So this is how assessment has been done. Now in this case, minor number 4, the design length of this minor is again 2 kilometer. The constructed length of this canal is 1.95 kilometer. So gap of only 0.05 kilometer. But the problem is that gap is very critical, because that gap is at the head reach, where the canal was supposed to connect to the main source. That connection is missing. So this canal, though it is completed 99.9%, will not receive water from the source, because that particular section is incomplete. So I can say the physical infrastructure is complete 99%, but the hydraulically connected length is 0 meter. So the irrigation potential achieved by this canal will be 0. Similarly, you can see here half of the canal is completed, so I can say only 50% IP is achieved. In this case, very less. The gap is very small, but the gap lies in the head reach. So the next very long canal which is physically completed will not get water. So only this much of canal will be considered as a hydraulically completed canal, and only this much length will be used to know how much is the IP generated. So now I was trying to show you how it appears in the satellite image. These blue lines are the canals digitized, and these are the pictures. So I was showing this is a Kangri left and Kangri right minor, and if you can see on the remote sensing data, this particular natural stream, the signature is continuous. Okay, had the now you can see here the canal passes over this natural stream, and you can see here the natural stream signature is getting broken here at this particular thing, which tells me that the main canal is continuous, and there is some cross drainage structure constructed here through which the natural stream is passing below this canal, and this canal is passing over this natural stream. Whereas here I can see the natural stream is, the signature is clear. So there could be two cases. One, the canal is incomplete, or the canal is passing this natural stream. Now to know this, we have to go for field visit. And when we have gone for field visit, what I see there is this kind of scenario where the natural stream has totally destructed the canal. The actual canal was constructed over the natural stream, and with time, with the flood events, the natural stream has destructed the canal, and that's why the stream is giving continuous signature and the canal is giving break signature. So I can mark this as a gap. Same thing is true for all other canals also. Wherever gap was there, you can see here now the canal is complete up to this, the canal is complete up to this, and there is no canal here. So this is a gap. Even here you can see this is the main source, this is a canal, and there is a missing link. No link is here. So I can say this is a gap. So all these kinds of gaps and canals we have mapped, even the gap lengths also we mapped. This one is a very particular example where the irrigation authorities told us that this particular miner is complete, this particular distributor is complete. But when we acquire the remote sensing data, if the canal is complete, I should get a signature even through this bright patch also. Whereas I am not getting that continuous signature, which tells me that there is some construction or alteration here. But because the irrigation authorities were claiming that this has been constructed for field visit, and what we could see there was this particular thing is the marking done other canal project authorities. This is actually their main canal alignment. Now to make that alignment, they will dig this kind of ditch at some particular 2 or 3 kilometer distance, and they have destroyed this distributory and minor canal. So actually this was constructed, but because of some other operations, now this is being destroyed. That's why we have to keep track of our irrigation infrastructure temporarily, dynamically. Now, when we have analyzed this entire project, as you can see, the ultimate irrigation project, irrigation potential of this project was 1 lakh, I think 5,000. Whereas the satellite derived irrigation potential created under this project was 88,393. So the report says that there is only gap of whatever report CWC or the irrigation authorities has given us. Those reports says that there is a gap of only 244 hectares of irrigation potential. Means out of total promised irrigation potential, if 244 hectares is not being constructed. Whereas the analysis done by us shows us that there is a tremendous gap. The balanced irrigation potential which we have derived using remote sensing data comes around something around 10,400 and something 475 or something like that, with 87 critical gaps. So the report says that there is no gap in this canal project, whereas we have mapped 87 critical gaps, so there is a balance of irrigation potential. And what we have done, every canal, every minor, every distributory branch canal, we have mapped, and we have tried to calculate how much is the balance IP. And with that, we have also given information that where the gap exists, is there a gap or the length is being shortened, and if there is a gap, what is the change of that gap, and what is the length of that gap. So this information is now important for next phase of project. As I told you in project cycle, the monitoring, the performance evaluation analysis goes as an input for next project. So this is a monitoring and performance evaluation animation. So now if I have to see in particular miner which one is the critical gap or how many gaps are there, so and how much length of gaps are there, so as to how much money I have to give them to complete these gaps, construct these gaps and achieve the entire IP. This kind of information is always helpful, which we have derived using remote sensing and GIS. So this is a table which we have prepared for all the canal in this Eastern Ganga project. So I'll skip to the final table here. This kind of map is being generated where every canal is being given different sign, every structure is being mapped, visible structure, then the gap is being mapped, and the area which is not getting water because of that critical gap is also being, if you can see here, this is balance IP boundary. This particular thing is a balance IP boundary, which tells me that because of this particular gap, this entire area is not getting the water. If I have this kind of apps ready, the decision makers can take decisions and they can support their decisions very easily. This is another case study for Madhya Ganga and Lower Ganga, which we will not discuss because it's the same repetition of same technique. And the report is available online also. If you just go to NRC website, this AIBP, all the reports, all the data is being given and is being distributed free of cost. Now, let us say we have discussed how to map the or how to calculate the irrigation demand, how to know how much water is available, then to map the irrigation infrastructure. But if everything is okay, I have to check that whether whatever I am doing, whatever operation I am doing in this irrigation command, is it actually giving me the desired output or not. In other sense, I have to evaluate the performance of my irrigation project. And why it is important, I'll quickly run through. As we all know, we have very good, we are blessed with the cultivated land, we are blessed with the amount of water that we get, and out of totally we get 4,000 billion cubic of water as a precipitation. Out of that, 1,123 is a utilizable water, which comes 690 comes from surface water and 433 comes from groundwater. So we total annual utilizable for India is 1,123. Please try to remember this figure because this will come in coming slides. Now you can see every irrigation project, whatever the area or the objective is, the project has to follow these essentials of good irrigation system. What are these essentials? The irrigation project should supply water adequately. So adequacy is the first essential. You should supply water efficiently so that water can be saved. So it's a second essential. The supply should be reliable. It should supply equitably and timely supply. So every irrigation project, regardless of its geographical location, its purpose, has to follow these essentials of irrigation. And if it follows these essentials of irrigation, it is a good irrigation project. But now, all these things, whatever we are discussing, are the qualitative terms. We have to convert these terms into quantifiable indices, so that if I am able to quantify them, I can tell that, okay, my project is performing well or not. Now, just to discuss what is the demand or what is the need of performance evaluation and improving the performance of the system, you can see by 2050, this is a projected population. And to feed that population, we have to increase our crop growth. We have to increase our crop production up to this level. And to increase this, we need more water. But on the contrary, by 2050, per capita water availability will just touch the water scarcity line. So something around 1,100 cubic meter is the water scarcity scenario, and we are touching that 2050. We will touch that because the available water resource for our country is limited. So the National Commission for Integrated Water Resource Development Plan has done this assessment that if the population growth scenarios, low, medium and high, are being considered, what will be the demand for water for irrigation. And as you can see, even if I consider the medium scenario with the medium population growth, by 2050, the agriculture itself will require 1,008 billion cubic meter of water. And if the high rate of population growth continues, we require 1191, where we have seen in previous slides that we only have 1123 billion cubic meter of water. So the demand by agriculture itself will exceed over the total water, utilizable water. Even with this amount, we cannot have a sustainable system because the primary demand which we have to satisfy is the irrigation water demand, the drinking water demand. After that, we have to satisfy the irrigation water demand, but parallelly we have to satisfy the industrial water demand also. And if I use this much of water for irrigation, there will be almost no water left to fulfill the demand for the urban cities, for its drinking, for its sanitation, for the industrial. So, what we have to do? We have to reduce the irrigation water demand by agriculture. And the only way out of the situation is by improving the efficiency of water used in the agriculture system. And to improve that, we need to know at what level we are performing right now. The solution could be by 25, all the surface irrigation projects should perform at 50% efficiency. And ground project should perform at 72% efficiency. By 2050, all surface irrigation projects should be performing at 60% efficiency level and groundwater projects should be performing at 75% efficiency level. Right now, the report says that, government report says that surface irrigation projects are performing at 35% irrigation level, efficiency level, and groundwater irrigation projects are performing at 65% efficiency level. Though this is over prediction because many of the projects in northern India are running at as low as 14% efficiency. So we have to elevate that. And the fact is irrigated agriculture is the largest but most inefficient user of fresh water. And this is universally accepted fact. You can see India, the share of irrigation is 83% in total utilizable water. But what government report says that all irrigation projects are presently running at 38 to 40%, and if I am able to increase my water use efficiency just by 10%, I can add 14 million hectares of land under irrigation with very minimal input, because I don't have to construct new project. I just have to improve efficiency of my existing project, and I can extend the IC irrigable command area of the same project, and I can increase total irrigable area by 14 million hectares. So the government claims that our projects are running at maybe 38 to 40%, and the remaining water, whatever water we are losing, is in other terms bad environmental effects like salinity, waterlogging. To check this, we have to improve our water use efficiency. And you can see the World Bank report says that though government is claiming we are running at 38 to 40% efficiency level, but the actual efficiency level that we are attaining is 20 to 35% only. So the way out would be, we have to improve. As we can see, the national activities proposed in the 11th plan clearly identifies that the efficiency study on completed major and medium irrigation projects and benchmarking of those projects based on their performance improvement. So the performance assessment of irrigation project is the only way out. We need to know at what level my project is performing. And to know the performance of my project, there is no other solution but remote sensing and GIS approach, because performance of a project needs to be analyzed at different levels. I need to know what is the performance of the project as a project as a whole. I need to know if there are 5 branch canals in my irrigation project, how each of the branch canal is performing. Now if each of the branch canal is supplying water to 3 distributaries, how that each distributary is performing, so that I can identify which component in my entire project is not performing well, so that I can concentrate my efforts on that component only. If all components are performing at same level, then okay, there is some policy decisions that I have to take. But always it happens that if there are 4, 6 or more components in the project, 2, 3 components will perform well, whereas only 1 or 2 components are not performing better. That's why your overall performance is coming down. So I have to first identify which are those components which I should focus on to improve my performance. So we'll discuss a case study here. We'll just skip this introduction because we don't have too much of time left. So I'll discuss this with the Upper Varda irrigation project performance evaluation. This is a command area in Vidarbha region of Maharashtra, Amravati and Varda district. So we have used remote sensing data here. We have used meteorological data, some field data, and some information from water resource Valmi, Aurangabad. So what are the RS derived parameters, remote sensing derived parameters? We have derived the canal network map from high resolution remote sensing data. We have derived land use map using multi-temporal, multi-space data. Then from field observations and this we have generated the KC map and we have calculated the irrigation water requirement, and that has been used as input for performance evaluation. As you can see, I will try, or we have tried to evaluate the project to know all essentials of good irrigation system. We will try to know whether the irrigation project is giving water adequately, efficient, is it equitable, is it timely, how it is performing physically, what is the agricultural performance, what is the economic performance, what is the environment. So all the essentials of good irrigation project we will try to quantify using different performance indicators. And this is a flow chart of this process, whereas the high resolution remote sensing data is being used to generate the database. The structure map using multi-temporal data, we have generated the land use map or crop type map and some ancillary information like the slope or the DEF has been used here. Now from that multispectral data, we have calculated the vegetation index from land use map and vegetation index, and field information we have generated the KC map. From metallurgical data, we have calculated the potential evapotranspiration, we have interpolated it, so we have now the pixel-based potential evapotranspiration, we have multiplied the KC with this, and we have derived the, as we have seen in first case, we have derived the crop water requirement. So as you can see here, this is a specially distributed points from where we have collected the, before this we have generated the land use map. In every crop type, we have selected something around 100 points randomly, and for those 100 points, we have extracted the NDVI value for all the months in the Rabi season, and the average of those all 100 values after statistical analysis and filtering is being mentioned here. So, if there is a gram crop, how the vegetation index will vary. If there is a vegetation crop, how the vegetation index will vary. For cotton, how it will vary. For red gram, how it will vary. And for the same crop, for the same months, we have calculated the KC value from Valmi. And using the technique which we have discussed in very previous section, first section of this presentation, we have generated the relation between vegetation index and KC. So now we will have KC map. So these are the relation between KC and vegetation index. So we have the KC map for all the months. We have the potential evapotranspiration for all these months. So we have multiplied the potential evapotranspiration with KC. So that we get the actual evapotranspiration or crop water requirement. We have added the crop water requirement for all the months in that season, so that we can get the crop water requirement of this entire season. So now we have this canal network. We know the boundary of that particular canal, to which area this canal supplies water, how much is the gross command area, how much is the cultivated command area, and how much is the irrigable command area of that particular canal. So we know how much is the crop area, what is the water demand, and then we have tried to compare this or calculate this performance indicators. Like to know adequacy, we have calculated 4 indicators. The first called relative water supply, which is nothing but this is the irrigation supply. This is the precipitation divided by potential evapotranspiration. It tells me that how much water is being given or available to the land and divided by its potential demand. So actually this should always be more than 1. Literature says it should always be more than 1.5 or 2. So you can see here, but first case it is more than 1.5. It should be more than 1. These cases it is more than 1. But these actually something is missing here. These cases it is less than 1. So I can say at least these 3 canals the water has been given adequately. Whereas remaining 3 canals the water is not being given adequately. But here actually the potential evapotranspiration is considered. Whereas potential evapotranspiration do not directly govern my crop. Actually the actual evapotranspiration governs my crop. So this index is being modified as relative water supply, which is nothing but irrigation water supply divided by the crop water requirement of my area minus the potential rainfall. So this is the demand. This is the demand, this is the supply, and this demand minus natural supply. So this gives me the actual value. This value should the range of 1.5 to 2. So these 3 are having more than 2. So now I can know here the water is adequate, maybe more than required. Here the blue is around 1. This is here, it's more than 1. This is near to 1. So I can say this here may be adequate, here may be borderline case. Now this is the depletion factor. So these kinds of indices we have calculated. We see all these indices in the final table. Then to know the crop productivity, agriculture performance, what I have done, I have collected, or you can collect the crop production information from your command and from your non-command area. And then you can compare. As you can see here, wheat per hectare production is 3 tons command area, whereas in non-command area is 1.89 ton. Where I can see there is a positive increase in productivity in the command area for all the major crops. So I can conclude that there is a positive impact of this project on agriculture system of this area. Now waterlogging and salinity, again we have collected samples and through farmers interview we have tried to analyze whether there is a problem of waterlogging and soil salinity in this area, and what we could see here is there is no problem of waterlogging and salinity. So I can conclude that the irrigation project has no problem, environmental problem. So its environmental performance is. Now to summarize, all performance indicators I have given in this table, where this performance indicator tells me that these three divisions, you can see their irrigation efficiency. It is way below than 0.65. It's very less, irrigation efficiency is very less. Whereas here irrigation is 0.92, I mean 92%. You cannot achieve 92% irrigation efficiency in surface irrigation system. The highest possible irrigation efficiency that you can achieve is 65 or 70%. So this is more unrealistic data, because what is irrigation efficiency? Irrigation efficiency is, you can say, the demand by supply. And because your demand is more and supply is less, this thing is getting towards your 100%. Now, these are the problem areas. Now this is, it's okay, 0.55 is physically achievable, 0.78 it is high, so there is some problem here. So these two are the sub-commands getting less water. These three are the sub-commands in excess water. And this is the perfect system, where actually the performance is 55%. You can see here, out of entire command, it is giving out of 6,227 hectares of area which this division was supposed to irrigate, it is only irrigating 2,204 hectares. So the irrigation ratio is only 35%. 33%, 40%, whereas here it is 63%, 65%. So these people or these divisions has to elevate this. They have to irrigate more of the area, so their efficiency will increase, their irrigation ratio will increase, and all these indices will come up so that the overall performance of that project will be better. Now, had I done this performance evaluation at a project level only, the only result that we can give is the particular project is not performing well. But then we cannot tell the decision maker that what is going wrong, which component is not performing well. If we do this at lower hierarchical levels, as lower possible, like you instead of doing the performance evaluation at a project level, go for branch level, go for distributory level. At that level, you can identify a particular branch or particular distributory or number of distributaries which are not performing well, and some sub-commands which are performing very well, so that now the decision makers can take decision that okay, so these are the components which we should now bring our focus to and change their operational schedule so that we can improve the performance of entire project. Now, the challenging part in performance evaluation is knowing the equity of distribution. There is no direct performance evaluation indicator to analyze the equity of water distribution. But scientists have tried, we have tried to actually use remote sensing data to know whether the water is being distributed equitably or not. What we have done, this is a there branch command, and using the Landsat data, we have mapped the land use, we have mapped the land surface temperature, vegetation index, and because we know that if the water is being distributed equitably, the vegetation index value of a particular crop in entire command should be same. The land surface temperature in entire command should be same, because land surface temperature is ultimately governed by the moisture available in the land. And if every land parcel in that command is getting its due share, it will be at almost same soil moisture level. So it will give same production or same vegetation vigor and same land surface temperature. So what we have done, this is a canal network. We have created buffer, maybe a 100 meter buffer, 500 meter buffer, then 1000 meter buffer, like that, 300 meter buffer. And in these buffers, we have placed 1500 points in every buffer. And for those points, we have extracted the vegetation index values, the land use type, and the LST value, and we have analyzed these values for every crop. for wheat, for other crop, what is the NDVI value, what is the LST value in different buffers. And this analysis, see, ideally, if my canal is supplying water adequately, within its command, the vegetation index of a particular crop and LST under that crop should be same. So there should be less deviation, there should be less variance. So we have tried to calculate the standard variation and standard deviation, CV and standard deviation, and what we could conclude here is because the CV and ST values were almost negligible, so we can conclude that the equitable distribution is there. But the problem here, catch here is, in northern India, the source of irrigation is canal because the rivers are perennial and all the seasons you receive water from canal. Whereas in central India and south India, the rivers are not perennial. So the canal supply will be limited to a particular season or 2 seasons. Particularly in summer season, you will not get water from the canal, and farmers within the command have now constructed their private tube well or community tube well through which they pump the groundwater for irrigation when they don't receive water from the canal. So now it is very difficult to distinguish between water from used from surface source or groundwater. Now to do that, we need more GIS database, which is a laborious task. But still, remote sensing can help you in mapping the canal network, mapping the crop type, knowing how much is the water demand, knowing how much is the water available, then knowing how your performance project is performing, and performing in all essentials of good irrigation system. So that's all from my side, where we have discussed application, few aspects of application of remote sensing in irrigation water management. Thank you.